far beyond Neptune, past Pluto, beyond the scattered icy debris of the Kuiper Belt, something may be moving. Not fast, not bright, not visible, but heavy. For years, astronomers have been tracking subtle gravitational fingerprints in the outer solar system, tiny deviations in the orbits of distant icy worlds. Objects that should be scattered randomly are strangely aligned, almost as if something massive is guiding them. A planet, not yet seen, not yet confirmed, but mathematically persistent. In tonight's journey, we explore the evidence for Planet 9, the hidden giant that may still be orbiting the Sun in deep darkness. We'll follow the real data, the orbital mechanics, the computer simulations, and the limits of our telescopes. No exaggeration, no speculation beyond physics, just the quiet possibility that our solar system is not finished revealing itself. Welcome back to Theories Before Sleep. Let's begin. In astronomy, revolutions often begin quietly, not with explosions in the sky, not with sudden images from a telescope, but with numbers that do not sit comfortably. Planet 9 did not begin as a photograph. It began as an inconsistency, a pattern that should not have existed. Far beyond Neptune, the solar system does not end. It thins out. It becomes sparse, cold, and dark. The Kuiper Belt stretches outward, filled with icy remnants from the era when planets were forming. Beyond that lies an even more distant region, sometimes called the scattered disk. Objects flung outward long ago by gravitational interactions. These distant bodies move slowly. A single orbit around the Sun can take thousands of years. And because they move slowly, their positions preserve history. That is what makes them important. In the early 2000s, astronomers began identifying objects with extremely elongated orbits, what we call extreme trans-Neptunian objects, or ETNOs. These objects travel far beyond Neptune, sometimes reaching hundreds of astronomical units from the Sun. One astronomical unit is the distance between Earth and the Sun. Neptune orbits at about 30 astronomical units. Some of these objects reach 300, 400, even more. At those distances, sunlight is faint. The Sun appears like a bright star in a black sky. Temperatures drop to near absolute zero. And yet, these objects move in very specific paths. When astronomers mapped the orbits of a small group of these distant bodies, they noticed something unexpected. Their orbits were clustered, not randomly oriented, as gravity from known planets would suggest, but aligned in a peculiar way, their elongated paths all pointing roughly in the same direction. Imagine tossing several pebbles into a pond and finding that every ripple forms the same shape, all angled toward one invisible source. That alignment should not persist naturally. Over billions of years, gravitational interactions with the giant planets, especially Neptune, should scatter those orientations randomly. The solar system is chaotic enough that long-term alignments tend to dissolve. But here, the clustering remained, subtle, not dramatic, but statistically unlikely. In 2016, two astronomers, Konstantin Batygin and Mike Brown, analyzed this alignment more deeply. Instead of dismissing it as coincidence, they asked a question. What kind of gravitational influence would be required to keep those orbits aligned? They ran simulations. In these simulations, they introduced a hypothetical planet, a large one, several times the mass of Earth, orbiting far beyond Neptune. When this planet was included in the model, something remarkable happened. The clustering appeared naturally. The distant icy objects behaved exactly as observed. Remove the hypothetical planet, and the alignment dissolved over time. Keep it, and the structure persisted. That was the first serious argument for Planet 9. Not an image, not a detection, a gravitational explanation. The proposed planet would not be small. It would likely be between 5 and 10 times Earth's mass. That places it in the category of a super-Earth, a type of planet common around other stars, but not represented in our own inner solar system. Its orbit would be enormous. Estimates suggest a semi-major axis of perhaps 400 to 800 astronomical units. Its orbital period could range from 10,000 to 20,000 years. That means if Planet 9 exists, it moves so slowly that over a human lifetime, it would barely shift against the background stars. And it would be faint, extremely faint. At such distances, sunlight is weak. A planet that far out would reflect only a tiny fraction of light toward Earth. Even large telescopes might struggle to see it unless pointed exactly in the right region of the sky. This is why Planet 9, if real, has not already been found. But the alignment of extreme trans-Neptunian objects was not the only clue. Another strange observation emerged. Some of these distant objects had orbits tilted significantly relative to the plane of the solar system. A few even appeared to have retrograde orbits, moving opposite the direction of most planets. In simulations including Planet 9, these unusual inclinations were reproduced naturally. The gravitational influence of a distant, massive planet could shepherd objects into these tilted configurations over millions of years. Without such a planet, the mechanism for creating those extreme inclinations becomes less clear. Now, it is important to remain cautious. Astronomy is full of patterns that later dissolve with more data. The number of known extreme trans-Neptunian objects is still relatively small. Observational bias plays a role. Telescopes tend to search certain regions of the sky more than others, and faint objects are easier to detect in some areas than in others. Could the alignment be a result of where we have looked? Some researchers argue the possibility cannot be ruled out. Statistical significance depends heavily on sample size. With more discoveries, the pattern might weaken. But as of now, the clustering remains intriguing. And that is what makes Planet 9 compelling. It is not based on speculation alone. It is based on orbital mechanics. Gravity leaves fingerprints. We discovered Neptune in the 19th century because Uranus's orbit did not match predictions. Mathematicians calculated that another planet must be tugging on it. Neptune was found near the predicted position shortly afterward. Planet 9 would not be identical to that story. The outer solar system is more complex. The distances are vastly greater, but the principle is similar. When orbits deviate systematically, something is exerting influence. If Planet 9 exists, it may not have formed where it now resides. One hypothesis suggests that during the early chaotic period of planetary formation, gravitational interactions between the giant planets, Jupiter, Saturn, Uranus, and Neptune, could have scattered a super-Earth outward. Instead of ejecting it completely into interstellar space, the Sun may have retained it in a distant, elongated orbit. Another possibility is capture. The Sun was likely born in a cluster of stars. During those early millions of years, stellar neighbors pass relatively close. It is conceivable that the Sun captured a planet from another system. Though this scenario requires precise conditions, both formation pathways remain under investigation. What is clear is this: if Planet 9 exists, it would reshape our understanding of the solar system's architecture. For decades, textbooks have described 8 planets orbiting within 30 astronomical units, with dwarf planets and icy debris beyond. But a super-Earth lurking hundreds of astronomical units away would expand that map dramatically. It would mean our solar system contains a class of planet common elsewhere, but hidden from us until now. And yet, despite the excitement, Planet 9 remains hypothetical. No direct detection, no confirmed image, just gravitational traces. In the next part, we will explore how astronomers are searching for it, which telescopes are involved, how sky surveys scan enormous regions of darkness, and why even a large planet can remain invisible in the vast outer reaches of our solar system. Because sometimes the hardest thing to see is something moving almost, not at all. The search for Planet 9 is not a matter of pointing a telescope at one location and waiting. It is a patient survey of darkness. If this planet exists, it does not glow with internal heat like a star. It does not reflect bright sunlight like Jupiter. At hundreds of astronomical units from the Sun, even a large planet would be dim, perhaps thousands of times fainter than Pluto appears in our sky. And Pluto itself is already difficult to detect without powerful instruments. To understand the challenge, imagine standing in a desert at night. The landscape stretches for hundreds of kilometers. Somewhere in that darkness is a moving object the size of a small mountain. It reflects only a faint glimmer of distant light, and it moves so slowly that from one night to the next, it barely shifts. That is the problem astronomers face. The sky is vast. Even narrowing the search to likely regions based on orbital modeling leaves thousands of square degrees to scan. Early on, researchers used data from existing sky surveys, large projects designed to map the heavens systematically. One of the most important has been the Subaru telescope in Hawaii. Its Hyper-Suprime Cam instrument can capture wide-field images of the sky with extraordinary sensitivity. Mike Brown and colleagues have spent years using Subaru to search the predicted regions where Planet 9 might be located. The strategy is straightforward in principle. Take images of the same region of sky over multiple nights and look for objects that move relative to the background stars. But in practice, it is complex. Stars are fixed on human timescales. Distant galaxies are effectively stationary. But objects within the solar system move slightly from night to night due to their own orbital motion and Earth's movement around the Sun. For near-Earth asteroids, that motion is obvious. They streak across images. For objects in the Kuiper Belt, motion is slower. For something at 600 astronomical units, motion is extremely subtle. It may shift only a few arc-seconds over days. Detecting that requires precision, calibration, and repeated observations. And then there is brightness. Planet 9, depending on its size and reflectivity, could be around magnitude 22 to 25, extremely faint. Many telescopes can reach that sensitivity, but only with long exposures and careful data processing. Astronomers must filter out noise, cosmic rays striking the detector, background galaxies, instrumental artifacts, variable stars. Each candidate must be tracked over time to confirm real motion. The search is slow, and so far, no confirmed detection. But the search has already revealed something important. We are finding more extreme trans-Neptunian objects. Each new discovery either strengthens or weakens the alignment pattern. So far, the clustering persists. Not perfectly, not dramatically, but enough to remain statistically interesting. Meanwhile, alternative explanations have emerged. Some researchers suggest that instead of one large planet, the clustering might arise from the collective gravitational influence of many smaller objects in the distant Kuiper Belt, a distributed disk of mass. If enough small bodies exist beyond Neptune, their combined gravity could produce similar orbital effects. However, simulations suggest that achieving the observed alignment through distributed mass alone would require more material than current observations support. Another proposal involves observational bias. Perhaps telescopes have disproportionately surveyed certain areas of the sky, creating an artificial clustering effect. This is a valid concern. Astronomical surveys are not perfectly uniform. Weather, instrument availability, and research priorities all shape where we look. To address this, teams simulate survey coverage, modeling how likely it would be to detect objects in different orientations. Some studies argue that bias may account for part of the clustering. Others conclude it cannot fully explain it. The debate continues. Science at this stage is not about certainty. It is about narrowing possibilities. While optical searches continue, another approach considers infrared observations. Even far from the Sun, a planet retains some residual heat from formation. It cools slowly over billions of years. That internal heat could emit faint infrared radiation. NASA's WISE, Wide Field Infrared Survey Explorer, scanned the entire sky in infrared wavelengths. Data from WISE have been analyzed to search for distant massive objects. So far, no clear Planet 9 has appeared, but the limits of detection depend on assumptions about the planet's size, temperature, and reflectivity. If Planet 9 is smaller or darker than expected, it may remain below detection thresholds. Future surveys may change that. The Vera C. Rubin Observatory, currently under construction in Chile, is expected to revolutionize time-domain astronomy. Its Legacy Survey of Space and Time, LSST, will scan the entire southern sky repeatedly with unprecedented depth and coverage. This observatory could detect faint, slow-moving objects far beyond Neptune. If Planet 9 exists in accessible regions of the sky, Rubin may find it within the coming decade. But even without detection, the modeling has deepened our understanding of the outer solar system. The gravitational interplay between Neptune and distant objects is more complex than once thought. Resonances, secular interactions, and long-term orbital evolution shape this distant frontier. Planet 9, whether real or not, has forced astronomers to examine these dynamics more carefully. And then there is a broader implication. If a super-Earth exists in our solar system, it would challenge the apparent uniqueness of our planetary layout. Most exoplanet systems discovered around other stars contain super-Earths, planets between Earth and Neptune in size. Our solar system does not appear to, unless one has been hiding in darkness all along. This possibility reshapes how we compare ourselves to other systems. Perhaps our solar system is not missing a super-Earth. Perhaps it is simply distant. Still, caution remains essential. Extraordinary claims require extraordinary evidence. Until a telescope captures a moving point of light that matches predicted motion and brightness, and until its orbit is confirmed, Planet 9 remains hypothetical. But hypothetical does not mean imaginary. It means unconfirmed. The mathematics remains compelling enough to justify continued search, and so astronomers keep scanning, night after night, image after image, comparing frames taken weeks apart, looking for a faint dot that shifts slightly against the stars. If Planet 9 exists, it will not reveal itself dramatically. It will appear as a subtle movement, a confirmation of gravitational whispers, first noticed in orbital diagrams. In the next part, we will step further back and ask a deeper question. If Planet 9 is real, how would it have shaped the history of our solar system? Because a planet that massive, even far away, does not remain irrelevant. Over millions and billions of years, gravity sculpts everything. And if something large has been orbiting quietly in the darkness, its influence may already be written into the architecture of the outer solar system itself. If Planet 9 exists, it has not simply been drifting quietly at the edge of the solar system. It would have been shaping it. Gravity does not require proximity to matter. It requires mass, and over millions of years, even a distant gravitational pull can rearrange entire regions of space. To understand this, we need to think not in years, but in epochs. The solar system is 4.5 billion years old. That is enough time for small gravitational nudges to accumulate into large structural changes. If a planet 5 to 10 times the mass of Earth has been orbiting hundreds of astronomical units away for billions of years, its influence would be subtle, but persistent. And persistence is powerful. Let us begin with the Kuiper Belt. The Kuiper Belt is not a uniform disk. It contains gaps, clusters, resonances, and scattered objects. Neptune plays a major role in shaping it. Through gravitational interactions and orbital resonances, Neptune shepherds many objects into stable configurations. But Neptune's influence weakens with distance. Beyond roughly 50 astronomical units, its gravitational grip fades significantly. And yet, the outermost objects, those extreme trans-Neptunian objects, show structured behavior. Their perihelia, the closest point in their orbit to the Sun, are lifted. Instead of dipping close to Neptune, they remain distant. This is unusual. Neptune alone should not be able to maintain that separation over billions of years. Simulations show that a distant massive planet could act as a gravitational anchor, stabilizing those elongated orbits and preventing close encounters with Neptune. Over time, Planet 9 would sculpt a region of space where certain orbital paths are favored and others are destabilized. In effect, it would create invisible boundaries. Now imagine the early solar system. The giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form exactly where they are today. Evidence suggests they migrated. Jupiter may have moved inward before shifting outward again. Neptune likely migrated outward significantly. This migration would have scattered countless icy bodies. Some were ejected entirely into interstellar space. Some were flung into elongated orbits. If Planet 9 formed closer to the Sun, it might have been one of those scattered worlds, pushed outward by gravitational interactions with the giants. Instead of escaping entirely, it could have settled into a distant, stable orbit. If that happened, Planet Nine's presence would be a relic of a violent past, a survivor of planetary rearrangement, and that has implications. Its orbit, if highly elongated, would mean that for part of its journey, it comes closer to the Sun, perhaps 200 or 300 astronomical units, and then retreats to much greater distances. During closer passes, its gravitational influence would intensify in certain regions of the outer solar system. It could stir up comets. It could alter the distribution of icy bodies. Some researchers have even proposed that periodic comet showers in Earth's distant past might correlate with the gravitational influence of a distant massive object. This idea remains speculative, but the principle is grounded in physics. Gravity accumulates. Now consider orbital inclination. If Planet Nine's orbit is significantly tilted relative to the plane of the solar system, it could explain why some distant objects have unusual orbital tilts. The solar system is not perfectly flat, but most planets orbit within a few degrees of a common plane. Extreme tilts are rare, yet some distant bodies exhibit pronounced inclinations. A distant massive planet on a tilted orbit could gradually torque those objects, slowly pulling their orbits into alignment with its own plane. Over millions of years, that torque becomes visible in orbital data. Another intriguing effect involves long-term stability. Simulations suggest that with Planet 9 included, the outer solar system exhibits chaotic but structured behavior. Without it, some objects' orbits become unstable over billions of years. In other words, Planet 9 might not only explain clustering, it might help preserve certain orbital configurations. There is also the question of dwarf planets. Beyond Pluto, objects like Sedna and 2012 VP113 have extremely distant, elongated orbits that are difficult to explain with Neptune alone. Sedna, in particular, has a perihelion around 76 astronomical units, far beyond Neptune's strong influence. How did Sedna acquire such an orbit? One explanation is that it was perturbed by a passing star during the Sun's birth cluster phase. Another is that a distant massive planet shepherded it into that configuration. If Planet 9 exists, it may be the key to understanding Sedna's origin, and Sedna may be only one example of a larger population. Some models predict that if Planet 9 is real, there should be additional distant objects yet undiscovered, following specific orbital patterns. These predictions are testable. As more surveys expand, astronomers will compare new discoveries to model forecasts. Agreement strengthens the case. Disagreement weakens it. Now step even further outward. The Oort cloud, a vast spherical shell of icy bodies extending thousands of astronomical units, marks the outermost boundary of the Sun's gravitational domain. Planet 9 would lie far inside the Oort cloud, but closer to it than any known planet. Its gravitational presence could influence how comets are transferred between the scattered disk and inner solar system. Over billions of years, it might subtly alter the rate at which long-period comets approach the Sun. These are long timescales, nothing dramatic, but planetary architecture is defined by slow processes. If Planet 9 is there, it is not just another object. It is part of the framework. And frameworks matter. They determine stability. They determine distribution. They determine history. This brings us to a broader philosophical point. our solar system once appeared orderly and complete. 9 planets, then 8. Asteroids between Mars and Jupiter, Kuiper Belt beyond Neptune, Oort cloud beyond that. But as observations deepen, structure becomes complexity. The outer solar system is not empty, it is dynamic, and Planet 9, if confirmed, would represent the final major structural addition, a planet not lost, not destroyed, not ejected, but simply distant, hidden by scale. In the next part, we will consider how Planet 9 compares to other worlds we have discovered around distant stars, and what its existence would mean for our place among planetary systems. Because the possibility that we have overlooked an entire class of planet in our own backyard changes something fundamental. It suggests that even after centuries of astronomy, the solar system is still unfolding. If Planet 9 exists, it would not simply be another distant body orbiting the Sun. It would be something our solar system was thought not to have, a super-Earth. For decades, as astronomers began discovering planets around other stars, a pattern emerged. Many star systems contain planets between the size of Earth and Neptune, worlds larger than our planet, smaller than the ice giants, often rocky or with thick atmospheres. These super-Earths and mini-Neptunes are among the most common types of planets in the galaxy. And yet, our solar system seems to lack one. Between Earth and Neptune, there is a gap. No planet fills that intermediate mass range. Mercury, Venus, Earth, and Mars are small and rocky. Then come the giants, Jupiter and Saturn, followed by the ice giants, Uranus and Neptune. Nothing in between. For a long time, that absence made our solar system appear unusual. But if Planet 9 exists, it may fit precisely into that missing category. A world 5 to 10 times the mass of Earth would be larger than any terrestrial planet here, but smaller than Uranus and Neptune. It could be rocky with a thick gaseous envelope, or it could be icy, more similar to a scaled-down Neptune. Its composition remains unknown, but its very existence would align our solar system more closely with what we see elsewhere in the galaxy, and that has consequences. When astronomers model planetary formation, they simulate how disks of gas and dust around young stars condense into planets. In many simulations, super-Earths form naturally and often migrate inward toward the star. Our solar system's architecture suggests a different outcome. Perhaps Jupiter's early migration disrupted the formation or inward movement of such planets. But if a super-Earth was instead scattered outward, it changes that narrative. It suggests we did form one. We simply displaced it. Now imagine Planet 9 during the solar system's early history. If it formed closer to the Sun, it would have existed within a dense disk of gas and planetesimals. Interactions with Jupiter and Saturn, both massive and dominant, could have destabilized its orbit. Planetary scattering is not gentle. A close gravitational encounter between massive bodies can dramatically alter trajectories. One planet may gain energy and move outward. Another may shift inward. In extreme cases, planets are ejected entirely into interstellar space. If Planet 9 survived such an encounter but remained gravitationally bound to the Sun, it would settle into a highly elongated orbit. That orbit would be stable if sufficiently distant from the major planets, but not circular, not simple. Its perihelion, closest approach to the Sun, might still be hundreds of astronomical units away. Its aphelion could extend much farther, At such distances, interactions with the inner planets would be negligible, but its influence on the outer debris disk would be significant. There is also another possibility. Planet 9 might not have formed here at all. During the Sun's earliest phase, it likely resided in a stellar nursery, a cluster containing dozens or hundreds of newborn stars. These stars were much closer together than they are now. In that crowded environment, gravitational interactions between stars were more common. If another star passed sufficiently near, it could have exchanged material with the Sun's protoplanetary disk or even transferred a planet. Capture scenarios require precise conditions. The passing star must approach slowly enough for gravitational capture to occur. The planet must not be too tightly bound to its original star. The geometry must align favorably. While unlikely, it is not impossible. If Planet 9 were a captured world, it would carry a history from another stellar system. That possibility is profound. It would mean that part of our solar system originated elsewhere. But at present, formation via scattering remains the more widely considered explanation. Now consider its physical nature. At hundreds of astronomical units from the Sun, Planet 9 would be extremely cold. Surface temperatures might hover around -220 degrees Celsius or lower. Any atmosphere it retained would likely be composed of hydrogen and helium, possibly methane and other volatiles. In such cold conditions, gases condense. Clouds might form from exotic compounds. The planet would not shine brightly in visible light, but it might emit faint infrared radiation from residual internal heat. If it is 5 to 10 Earth masses, its gravity would be strong enough to retain a substantial atmosphere. It would not resemble Earth. It would resemble a distant, dimmed Neptune, but smaller, slower, quieter. Its orbital period might be 15,000 years. That means since the dawn of recorded human history, it would have barely moved along its path. Even civilizations rise and fall faster than that. Planet 9 would be a monument to long timescales. Now return to observational reality. If this world exists, it must occupy a specific region of sky consistent with orbital modeling. Each year, as Earth orbits the Sun, our viewing angle changes slightly. That allows astronomers to refine possible positions. The search narrows, but the sky remains vast, and faint objects are easily lost among countless distant galaxies. One key constraint is that Planet 9 cannot be too bright. Otherwise, it would have already been detected in past surveys. It also cannot be too close, or its gravitational influence would be stronger and more obvious. The sweet spot for its orbit must match both dynamical modeling and observational absence. That delicate balance makes the hypothesis testable, and that is important. A good scientific theory makes predictions. Planet 9 predicts clustering of extreme trans-Neptunian objects, specific inclination distributions, certain resonant behaviors, and eventually a detectable moving object in a particular region of sky. If future data contradict those predictions, the hypothesis will fade. If they confirm them, a new planet will join the solar system. But what would confirmation truly mean? It would expand the solar system's known boundary outward dramatically. It would add a new major body, not a dwarf planet, not debris, but a true planet. And it would remind us of something humbling. Even after centuries of telescopes, after spacecraft flybys of every major planet, after mapping asteroids and comets, we might still have missed something large, not because it was hidden intentionally, but because distance is deceptive. The solar system is not a compact arrangement. It is mostly empty space, and in that emptiness, something the size of a super-Earth could remain undetected simply because we have not looked deeply enough in the right direction. In the next part, we will explore what happens if Planet 9 is not found, and what that would mean for the strange orbital patterns that began this story. Because absence can be as revealing as discovery, and sometimes solving a mystery requires accepting that the answer is different than we first imagined. There is a possibility we have to face. Planet 9 may not exist. The mathematics may be elegant. The simulations may be compelling. The clustering may appear statistically significant. And yet, nature does not owe us confirmation. If years pass and no planet is found in the predicted regions of the sky, the question does not disappear, it shifts. Because the orbital patterns that inspired the hypothesis remain real observations, the extreme trans-Neptunian objects are not imaginary. Their unusual alignments, lifted perihelia, and inclined orbits exist in the data. So if there is no hidden planet, what else could be shaping the outer solar system? One possibility is that our sample size has simply been too small. Astronomy at extreme distances is limited by detection bias. Telescopes tend to scan certain regions of the sky more often than others. Faint objects are easier to detect when they are near perihelion, the closest part of their orbit, because they are slightly brighter there. That means we are more likely to find distant objects when they are clustered in specific positions relative to Earth. If most discoveries occur in overlapping survey areas, alignment may appear stronger than it truly is as more sky is scanned, particularly with the upcoming Vera C. Rubin Observatory. The sample of extreme trans-Neptunian objects will grow. If their orientations begin to randomize with new discoveries, the clustering may weaken naturally. In that case, Planet 9 would not be needed. Another explanation involves collective gravity. Instead of a single large planet, perhaps there exists a distant disk of small bodies, a massive, extended population beyond the Kuiper Belt. If enough material exists far from Neptune, its combined gravitational influence could subtly shape orbital distributions. But this requires more mass than current surveys suggest is present. Still, our knowledge of the outermost solar system remains incomplete. There may be populations we have not yet detected. There is also the possibility of stellar perturbations. In the Sun's early history, nearby stars within its birth cluster could have influenced the orbits of distant icy bodies. A passing star does not need to collide with the solar system to cause disruption. Even a relatively distant encounter can distort the outer disk, lifting perihelia and altering orbital inclinations. If such an encounter occurred early on, its effects could persist for billions of years. Sedna's orbit, in particular, has been cited as possible evidence of such a stellar encounter. In this scenario, the clustering we observe today would not require a present massive planet, but would instead be a fossil imprint of an ancient interaction. The solar system would be carrying the memory of its crowded infancy, and that memory would be written into the orbits of its most distant members. Another subtle possibility involves Neptune itself. Neptune's migration outward during the early solar system likely reshaped the Kuiper Belt dramatically. As it moved, it would have captured objects into resonances and scattered others into distant orbits. Perhaps the current clustering is a byproduct of that migration, not a separate gravitational shepherd. Some dynamical models attempt to reproduce observed patterns using only the known planets. Results vary. Some simulations can approximate parts of the clustering, but often not with the same coherence as when a distant massive perturber is included. But this is not a simple equation. The outer solar system is chaotic over long timescales. Small variations in initial conditions can produce large differences after billions of years, which means distinguishing between competing explanations is difficult. And that difficulty is part of the story. Planet 9 sits at the edge of detectability, not only physically, but statistically. The evidence is suggestive, but not overwhelming, and that makes it scientifically healthy. Because science advances most carefully when uncertainty is acknowledged. Now imagine the coming decade. The Rubin Observatory begins scanning the sky deeply and repeatedly. Thousands of new trans-Neptunian objects are discovered. If clustering strengthens, if patterns sharpen, the case for Planet 9 grows. If clustering dissolves into randomness, the hypothesis fades. Either outcome improves our understanding. If Planet 9 is not found, we will learn something important about orbital dynamics and observational bias. If it is found, we will redefine the solar system's architecture. There is another possibility worth considering. Planet 9 may exist, but not exactly as predicted. Its mass might be smaller than expected, its orbit more circular, its inclination different. Current models are constrained by limited data. As new discoveries emerge, parameters will shift. The predicted region of sky may move. Search strategies will adapt. This is not failure, it is refinement. Astronomy has a long history of predicted objects shifting before confirmation. Even Neptune's predicted position differed slightly from where it was ultimately found. And Pluto, once thought to be the predicted Planet X, turned out to be far too small to account for observed orbital discrepancies. History teaches patience. It also teaches humility. We once believed the solar system ended at Saturn. Then Uranus was discovered, then Neptune, then Pluto. Each edition expanded our map. Now we recognize Pluto as a dwarf planet, but its discovery opened the door to the Kuiper Belt itself. Planet 9, if confirmed, would not be a correction of orbital motion in the inner planets. It would be a revelation about the distant frontier. But if it is not there, the mystery remains valuable because it forces us to examine how gravity shapes structure over vast timescales. It forces us to confront the limitations of our observations. It reminds us that absence of evidence is not evidence of absence, but it is also not evidence of presence. So where does that leave us? In a space between certainty and speculation, a region defined by probability. Right now, the evidence for Planet 9 is plausible but incomplete. The clustering persists. The modeling supports a massive perturber. The sky remains partially unsearched. But until a faint dot moves against the stars in exactly the right way, the solar system officially contains 8 planets. Still, there is something compelling about the idea that something large could be orbiting quietly beyond our vision. Not hidden intentionally, just distant, just faint, just patient. In the next part, we will explore what it would mean, culturally and scientifically, if Planet 9 were finally detected. Because discovery is not just about adding a name to a list. It is about how we understand our place in space and whether we are truly finished discovering the structure of our own cosmic home. If Planet 9 is eventually detected, the moment will not look dramatic. There will be no sudden explosion of light, no bright new star flaring into view. Instead, it will likely appear as a faint point in a sequence of images. A tiny shift, a movement against the fixed background of distant stars. Confirmation will come slowly, through repeated observations, orbital calculations, verification from multiple telescopes, and then, quietly, the solar system will expand. Not physically, but conceptually, because for centuries, we have believed we understood the broad structure of our planetary system. 8 planets orbiting within a few dozen astronomical units, dwarf planets and icy debris beyond. Planet 9 would extend that structure outward by an order of magnitude. Its average distance could be 400, 600, perhaps even 800 astronomical units from the Sun. That is not just farther, it is a different regime of space. To put this into perspective, Neptune orbits at about 30 astronomical units. Pluto averages around 39. The Kuiper Belt stretches roughly from 30 to perhaps 50 or 60 astronomical units. Planet 9, if real, would orbit 10 times farther out than Neptune. That changes how we define the solar system's boundary. It would no longer feel like a compact system with a debris disk attached. It would feel layered. Inner rocky worlds, gas giants, ice giants, Kuiper Belt, scattered disk, and then a distant super-Earth in deep darkness. That layered structure resembles exoplanetary systems more closely than we once thought. Many stars host planets at large distances, often on eccentric orbits. Until recently, we believed our solar system lacked such architecture. Planet 9 would suggest otherwise. But beyond classification, there is something deeper. Discovery reshapes imagination. When Uranus was discovered in 1781, it doubled the known size of the solar system. Neptune's discovery in 1846 extended it further. Pluto in 1930 pushed the edge outward again. Each time, the public perception of how big our system is changed. Planet 9 would do that again. It would remind us that even our own neighborhood is not fully mapped, and that is humbling. Consider the technological implications. Detecting Planet 9 would require precise measurements and likely the most advanced sky surveys available. But studying it would require more. Spectroscopy to analyze reflected light, infrared measurements to estimate temperature, long-term tracking to refine orbital parameters, and eventually, perhaps decades from now, a spacecraft mission might be imagined. Travel time would be enormous. At Pluto's distance, the New Horizons spacecraft took nearly 10 years to arrive. Planet 9 would be 10 to 20 times farther away. Reaching it would likely require propulsion systems beyond what we currently use for deep space missions. Yet the desire to explore would grow immediately after confirmation, because a super-Earth within our own solar system would be unprecedented. We have detected thousands of exoplanets in this mass range, but none close enough to study in detail. Planet 9 would offer a laboratory for understanding planetary formation and atmospheric evolution at intermediate mass scales. Its atmosphere, if thick and hydrogen-rich, could resemble that of a mini Neptune. Its interior could reveal how such planets retain heat over billions of years. Its magnetic field, if present, could inform us about dynamo processes in icy super-Earths. Even its surface, if visible through thin atmosphere, might show frozen methane plains or exotic ice formations unknown elsewhere. But even before any spacecraft arrives, the confirmation alone would rewrite textbooks. Children learning the solar system would once again count 9 planets. Though this time, the 9th would not be small and controversial like Pluto, but massive and distant. And that raises another quiet question. What do we call it? Planet 9 is a placeholder, like Planet X. Before Neptune's discovery, a formal name would eventually be proposed, perhaps drawn from Roman mythology, as tradition suggests. But naming would only follow confirmation. First, we must see it. There is also a psychological dimension. For decades, the solar system has felt thoroughly explored. Spacecraft have visited Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Asteroids have been sampled, comets have been landed upon. The sense of frontier has shifted outward toward exoplanets and distant galaxies. Planet 9 would bring the frontier back home. It would say, even here, in our own system, something large has remained unseen. Not because we were careless, but because scale is vast and distance hides. There is something poetic in that, a reminder that discovery does not end simply because we have looked for a long time. And yet, caution remains. Confirmation would not erase alternative explanations overnight. It would require rigorous orbital fitting to ensure the detected object matches predictions. Its mass would need to align with gravitational modeling. Its orbit must explain the clustering. If a planet is found but does not produce the expected dynamical effects, the mystery would continue in a new form. But let us imagine that it does match, that everything aligns. What then? The outer solar system would gain a new anchor. The architecture would become clearer. The extreme trans-Neptunian objects would have a gravitational shepherd. Sedna's orbit would have context. Inclined objects would make sense. Theoretical simulations would converge with observation, and our map would expand. Yet even in that moment of confirmation, something remains constant. Planet 9, if real, has been there all along, orbiting quietly for billions of years, while life evolved on Earth, while dinosaurs rose and fell, while humans developed telescopes. It has completed perhaps only a fraction of one orbit since multicellular life began. Its timescale dwarfs ours, and that perspective matters. Whether found tomorrow or never, Planet 9 represents something fundamental about science. We do not know everything, not even about our own planetary system. We infer from patterns, we test predictions, we revise models, and sometimes we discover that what seemed empty was simply distant. In the next part, we will explore one final dimension of this mystery. What if Planet 9 is not the only hidden structure in the outer solar system? Because once we accept that large bodies can remain unseen at extreme distances, the boundary between known and unknown becomes less defined, and the darkness beyond Neptune begins to feel less empty than we once believed. If Planet 9 exists, it may not be the only surprise waiting in the darkness. The outer solar system has long been treated as a boundary, a fading edge beyond Neptune, where debris thins and gravity weakens. But that view is increasingly outdated. What lies beyond Neptune is not emptiness. It is structure. It is slow motion. It is history preserved in frozen orbit. And if one massive planet can remain undetected at hundreds of astronomical units, it forces us to reconsider what else might be hidden in that vast region. To understand this possibility, we need to expand our perspective again. The Kuiper Belt is only the beginning. Beyond it lies the scattered disk, objects whose orbits have been stretched and flung outward by gravitational interactions. Primarily with Neptune, these bodies travel in elongated paths. They can take them hundreds of astronomical units from the Sun. Even farther out lies the inner Oort cloud, a vast reservoir of icy bodies that extends thousands of astronomical units into space. We have never directly imaged the Oort cloud. Its existence is inferred from the behavior of long-period comets that occasionally enter the inner solar system. Those comets, with orbital periods of tens of thousands of years, originate from enormous distances. And yet, we assume this structure is smooth, uniform, spherical. But what if it is not? What if there are additional concentrations of mass in the distant solar system? Planet 9 already challenges our sense of completeness. If it exists, it implies that our census of large bodies is incomplete at extreme distances. The gravitational modeling that led to Planet 9 was not searching for novelty. It was responding to anomalies. That means the outer solar system still has the capacity to surprise us through orbital irregularities. Now consider how difficult detection becomes as distance increases. Brightness decreases with the square of distance. At 400 astronomical units, reflected sunlight is extremely faint. At 800, fainter still. And yet gravity does not diminish so quickly in its ability to shape trajectories over millions of years. That imbalance, faint visibility but persistent gravitational influence, creates the conditions for hidden structure. If Planet 9 is real, its mass might be 5 to 10 Earth masses. But what if there are smaller bodies, perhaps Mars-sized or Earth-sized, even farther out? Such objects would be extremely difficult to detect optically. They might emit weak infrared radiation, but surveys would need to reach extraordinary sensitivity to capture them. Could there be more than one distant perturber? Current modeling typically includes a single massive planet to explain observed clustering. But the outer solar system's evolution has likely been chaotic. Planetary scattering, stellar encounters, and resonance shifts over billions of years may have produced multiple survivors in distant orbits. We do not see evidence for several large bodies at present, but absence of detection at these distances is not definitive. And then there is another frontier: free-floating planets. Astronomers have discovered that the galaxy contains rogue planets, worlds not bound to any star. They drift through interstellar space, invisible except through rare gravitational micro-lensing events. If rogue planets exist in such abundance, it is reasonable to ask whether the Sun may have captured one or more during its early history. Capture events are rare but possible, particularly in dense stellar nurseries. Planet 9 itself has been hypothesized as a captured body in some models. But capture is not limited to one object. The early solar system may have been dynamically complex in ways we are only beginning to appreciate. There's also the matter of orbital stability. Long-term simulations show that distant objects can reside in stable niches for billions of years, even on highly elongated or inclined orbits. Some may never approach the inner solar system. They may remain in regions where detection is difficult. This raises a philosophical question. At what distance do we consider something part of the solar system? If an object orbits the Sun with a period of 50,000 years at 1,000 astronomical units, it is gravitationally bound. It is part of the system. But practically, it may be almost invisible. The solar system then becomes less like a compact family of planets and more like a gravitational domain, a territory defined by the Sun's influence extending far beyond visible structure. Planet 9, if real, sits within that domain but near its frontier. It forces us to imagine that frontier more vividly. And once imagined, it becomes harder to assume it is empty. There is also a deeper lesson here. The discovery of Neptune was not the end of outer solar system surprises. Pluto followed, then the Kuiper Belt, then dwarf planets like Eris and Makemake. Each discovery expanded the narrative, not because the solar system changed, but because our instruments improved. Planet 9 may be part of that progression, and if so, it will not be the final step. The Rubin Observatory will not only search for Planet 9, it will catalogue countless faint, distant objects. Patterns may emerge that we cannot currently predict. Some may confirm existing models. Others may challenge them. Our outer solar system is a slow laboratory. Its processes unfold over millions of years. We observe only a snapshot. But from that snapshot, we infer structure, and structure often hints at deeper complexity. Even if Planet 9 is eventually ruled out, the search itself will leave behind a richer map of distant space. We will know more about orbital distributions, more about inclination statistics, more about resonant structures. The absence of Planet 9 would not return us to simplicity. It would simply shift our explanations. In the end, what makes this mystery compelling is not just the possibility of one hidden planet. It is the recognition that our solar system's edges are not fully known. We have explored the inner regions in detail. We have sent spacecraft to the major planets, but the far outer reaches remain largely theoretical, and theory invites revision. If Planet 9 is found, it will not close the book. It will open it wider, because it will confirm that even large bodies can hide in the scale of cosmic distance, and if they can hide once, they can hide again. In the next part, we will turn inward again, examining how the existence or absence of Planet 9 reshapes our understanding of planetary formation itself. Because at the deepest level, this mystery is not just about what is out there. It is about how planetary systems come to be, and whether our own system is more typical or more unusual than we once believed. At its core, the mystery of Planet 9 is not only about detection, it is about formation. If a massive super-Earth truly orbits hundreds of astronomical units from the Sun, then we must ask a deeper question. How did it get there? Planetary formation is not random. It follows physical laws, gravity, angular momentum, thermodynamics, collisions. The early solar system was a rotating disk of gas and dust. Over time, particles collided, stuck together, and formed planetesimals. Those grew into protoplanets. Some accumulated gas envelopes, some remained rocky. In the inner solar system, temperatures were high. Volatile compounds evaporated. That is why Mercury, Venus, Earth, and Mars are rocky. Farther out, beyond the frost line, roughly 3 to 5 astronomical units from the Sun, temperatures were low enough for ices to condense. Water, methane, ammonia, these could freeze and contribute mass to forming planets. That allowed the rapid growth of large cores. Jupiter formed first, quickly accumulating gas and becoming massive. Saturn followed. Uranus and Neptune formed more slowly, likely migrating outward during the process. But between Earth and Neptune, we have no super-Earth. And yet, models of protoplanetary disks often produce them naturally. In fact, many simulations suggest that super-Earths are easier to form than systems like ours. This has puzzled astronomers for years. Why does our solar system lack a planet of 5 to 10 Earth masses close to the Sun? One explanation is Jupiter. Jupiter's early formation and possible inward migration may have disrupted the disk in ways that prevented super-Earths from forming or surviving in the inner region. The so-called Grand Tack model suggests that Jupiter moved inward toward Mars's current orbit before reversing direction due to interactions with Saturn. If true, this migration could have cleared out material and altered the growth environment of inner planets. But if a super-Earth formed early and was later scattered outward during gravitational interactions, then Planet 9 might be that missing body. It would mean our solar system did produce a super-Earth. It just did not remain in the inner region. This idea elegantly connects planetary formation theory with the Planet 9 hypothesis. But scattering is not gentle. For a planet to be pushed outward to hundreds of astronomical units without being ejected entirely, it must pass through a narrow window of gravitational energy exchange. Too much energy, and it escapes the Sun's gravity forever. Too little, and it remains too close to interact strongly with the Kuiper Belt. If Planet 9 exists, its orbit may preserve clues about that early instability phase. Its eccentricity, how stretched its orbit is, could indicate the intensity of the scattering event. Its inclination, how tilted it is relative to the solar system's plane, could reveal whether interactions were planar or chaotic. Its current perihelion distance, how close it comes to the Sun, could show whether Neptune still influenced it significantly after scattering. Each parameter becomes a fossil record of formation history. Now, consider the capture scenario again. If Planet 9 were captured from another star during the Sun's birth cluster phase, its orbit might be more randomly inclined. It could even be retrograde. Capture events are rare, but star clusters in early formation are crowded environments. Stars can pass within hundreds or thousands of astronomical units of one another. In such close encounters, gravitational exchanges can occur. If the Sun captured a planet, it would likely have happened within the first few million years of formation, before the cluster dispersed. If so, Planet 9 would be older than Earth's oceans, older than the Moon. It would have orbited quietly since before complex life ever arose. Whether formed here or captured, its existence would challenge the neat simplicity of planetary system diagrams. We often depict the solar system as orderly rings, but formation is chaotic. Collisions, ejections, migrations, resonances. The final architecture is the outcome of countless gravitational interactions. Planet 9, if real, would be a surviving witness of that chaos. Now expand outward again. if our solar system contains a distant super-Earth, it would align more closely with exoplanetary systems. Thousands of exoplanets have been discovered. Many systems contain super-Earths or mini-Neptunes at various distances. Some are tightly packed, some are eccentric, some are inclined. Our solar system appears somewhat atypical in lacking a close-in super-Earth. Planet 9 would suggest that we are not missing one. We simply misplaced it. That realization reshapes comparative planetology. It reduces the uniqueness of our architecture. It places us more squarely within galactic norms. But even if Planet 9 does not exist, the discussion itself has deepened planetary formation theory. The question forces us to refine migration models, to examine disk mass distribution, to consider the Sun's early environment, to simulate long-term orbital evolution with greater precision. In science, sometimes the hypothesis itself drives advancement, regardless of final outcome. Now consider long-term stability. If Planet 9 orbits at hundreds of astronomical units, it must remain stable over billions of years. Its orbit cannot intersect too closely with Neptune's domain. It cannot be so eccentric that stellar encounters easily destabilize it. Simulations show that certain orbital ranges produce long-term stability. Others lead to eventual ejection. If Planet 9 is stable today, it has survived countless perturbations, including passing stars in the Sun's galactic orbit. That survival would be remarkable because over billions of years, the Sun has orbited the Milky Way dozens of times. During those orbits, it has likely experienced occasional stellar flybys. Most distant objects are only weakly bound. A sufficiently close stellar encounter could strip them away. If Planet 9 remains gravitationally bound, it suggests its orbit lies within a stable zone, which again would constrain its possible parameters. In the end, Part 8 brings us to a central theme. Planet 9 is not merely a missing dot in the sky. It is a test of planetary formation theory. It is a probe into early solar system instability. It is a bridge between our system and the thousands of others we have discovered. Whether confirmed or refuted, it reshapes the conversation. Perhaps that is the most powerful aspect of this mystery. It reminds us that planetary systems are not static. They are histories written in gravity, and sometimes those histories leave gaps that invite us to look deeper. In the next part, we will step back one final time, exploring the philosophical dimension of hidden worlds and what Planet 9 represents in humanity's ongoing attempt to map the universe. Because beyond the equations and simulations, there is something profoundly human about searching for a world that might be there, just beyond the edge of light. There is something deeply human about searching for a world we cannot yet see. Planet 9 is not only a scientific hypothesis, it is a reminder of how discovery unfolds, slowly, cautiously, sometimes reluctantly. For centuries, the solar system felt complete. 8 planets moving in predictable paths. The outer boundary marked by Neptune, then extended by Pluto, then expanded conceptually by the Kuiper Belt. Each time we thought we had reached the edge moved. And now, once again, we find ourselves looking into darkness and asking whether something large might still be there. What makes this search unique is that it is not driven by curiosity alone. It is driven by gravitational evidence. We are not imagining a hidden world because we want one. We are considering it because orbital mechanics suggest something is exerting influence, and that is a powerful shift. In earlier centuries, unseen planets were proposed to explain discrepancies in the motion of known ones. Neptune was discovered this way. But Planet 9 is different. It does not reveal itself through the wobble of a visible planet. It reveals itself through the subtle choreography of icy fragments at the solar system's edge. That choreography is faint, but persistent. And persistence, in science, commands attention. There is also a philosophical layer here. The outer solar system exists beyond direct human experience. No human eye has seen it directly. Even spacecraft have only skimmed its inner edges. Beyond Neptune lies a region where sunlight is thin, motion is slow, and time stretches into tens of thousands of years. Planet 9, if real, would inhabit that regime of stillness. Its orbital period might be 15,000 years. That means the entirety of recorded human civilization, from the earliest cities to modern space telescopes, would occupy less than a fraction of one orbit. In other words, Planet 9's motion is nearly static relative to human history. It is almost timeless, and yet its existence or non-existence matters deeply to us. Why? Because mapping our system defines our place within it. Every new boundary forces us to reconsider scale. When Uranus was discovered, the solar system doubled in size. When Neptune was found, it expanded again. Each expansion humbled our assumptions. Planet 9 would extend that humility further. It would remind us that even after centuries of observation, something large can remain unseen simply because distance is deceptive. But even if Planet 9 does not exist, the lesson remains. The outer solar system is not empty. It is structured by gravity over immense timescales. We are only beginning to detect the faintest patterns within that structure, and that has implications beyond astronomy. It speaks to how knowledge works. We infer invisible forces from visible effects. We construct models. We test predictions. We refine. Sometimes we confirm. Sometimes we revise. Planet 9 sits precisely at that boundary between inference and confirmation. And that boundary is where science lives. There is also a caution embedded in this story. Throughout history, astronomers have proposed unseen planets to explain anomalies, sometimes correctly, sometimes not. In the 19th century, after Neptune's discovery, some scientists proposed additional planets to explain small irregularities in Mercury's orbit. That hypothetical planet was named Vulcan. It was never found. Instead, Einstein's theory of general relativity explained Mercury's motion without invoking a new planet. The lesson is clear. Not every anomaly requires a new object. Sometimes it requires a deeper understanding of existing laws. Planet 9 could follow either path. It could be confirmed, reshaping our solar system, or it could dissolve, leading to a better understanding of orbital bias and long-term gravitational evolution. Both outcomes are valuable because both increase clarity. Now consider something quieter. If Planet 9 is real, it has been orbiting silently for billions of years. It has seen the sun evolve gradually brighter. It has witnessed the formation of Earth's oceans. It has circled while life emerged, diversified, and contemplated the cosmos. And yet, it remains untouched. No spacecraft has passed near it. No instrument has captured its surface. It is, in a sense, pristine. That possibility evokes something subtle. The idea that even within our own gravitational domain, there are places untouched by exploration. It reminds us that exploration is incomplete, and incompleteness is not failure. It is invitation. The Rubin Observatory will soon scan the southern sky repeatedly and deeply. Its sensitivity will far exceed many previous surveys. If Planet 9 lies within its observational reach, the coming decade could resolve this question. If not, the search will continue with new strategies, because once a hypothesis reaches this level of plausibility, it does not simply vanish. It must be tested thoroughly, and that testing requires patience. There is no urgency in celestial mechanics. Orbits evolve over millions of years. The solar system does not change dramatically in human timescales, but our understanding of it can, rapidly. Planet 9, whether real or not, represents that shift. It marks the moment when we realized that the outer solar system might be more structured than assumed. It forces us to reconsider how far the sun's influence extends in meaningful ways. It reminds us that gravitational fingerprints can reveal what light does not. And perhaps most importantly, it keeps curiosity alive within our own neighborhood. We often look outward, toward exoplanets, toward galaxies, toward cosmic expansion. But sometimes, mystery remains closer than we think. Not close in distance, but close in belonging. Planet 9, if it exists, belongs to our solar system, and that makes the search personal. In the final part, we'll bring this journey to its conclusion, not with certainty, but with perspective, because whether we find Planet 9 or not, the search itself reveals something enduring about how we explore the universe, and about how the edge of the known is never fixed, only temporarily defined. There is a quiet beauty in a mystery that refuses to resolve too quickly. Planet 9 has not appeared in a telescope image. It has not been confirmed by infrared glow. It has not been tracked across the stars. And yet, it lingers, not as fantasy, not as science fiction, but as a gravitational possibility. Over the course of this journey, we have followed orbital alignments in the distant Kuiper Belt. We have explored simulations that reproduce clustering only when a massive unseen planet is added. We have examined alternative explanations, observational bias, stellar encounters, collective gravitational effects. We have considered formation models, scattering events, capture scenarios, and the broader context of planetary systems across the galaxy. Now, at the end, what remains is not certainty, it is perspective. The solar system is not a flat diagram in a textbook. It is a layered gravitational structure extending far beyond where the planets cluster. The inner worlds orbit tightly, bathed in sunlight. The gas giants dominate the mid-region. The Kuiper Belt marks the beginning of sparsity. Beyond that lies a frontier of slow-moving ice and ancient memory. Planet 9, if real, belongs to that frontier. It would not change life on Earth. It would not alter our orbit. Its gravitational influence on the inner solar system would be negligible, and yet its existence would reshape something fundamental, our sense of completeness. For centuries, astronomy has expanded boundaries outward. Each discovery pushed the horizon, but eventually we reached a plateau of familiarity. 8 planets, a belt of debris, a distant cloud of comets. Planet 9 unsettles that plateau. It suggests that even after mapping major bodies, something large could remain hidden simply because it moves slowly and reflects little light. And that possibility humbles us, because It reminds us how perception depends on scale. At hundreds of astronomical units, sunlight is faint, motion is slow, detection is difficult. A planet could orbit there for millennia unnoticed, not because we lack intelligence, but because distance reduces signal. This is a recurring theme in science. Large effects can remain hidden when their expression is subtle. Gravity leaves traces, light reveals surfaces, but at extreme distances, even light becomes sparse. Now consider what confirmation would mean. A faint dot detected in multiple exposures, carefully tracked over months, orbital parameters refined, mass estimated, inclination measured. It would not be a dramatic moment. It would be incremental. A press release, a paper published, a new entry added to planetary catalogues. But the impact would ripple outward. Textbooks revised, models updated, public imagination stirred, and quietly, a ninth planet would take its place in the narrative of our solar system. If that happens, we will have learned something profound. Not only that Planet 9 exists, but that inference from orbital patterns can reveal unseen structure, that gravitational fingerprints matter, that subtle clustering in distant debris can guide us toward major discoveries. But what if Planet 9 is never found? What if deeper surveys, broader sky coverage, and larger datasets dissolve the clustering pattern? What if alternative explanations prove sufficient? Then we will have learned something equally valuable, that statistical caution matters, that observational bias can shape perception, that early patterns may fade as data accumulates. Science does not suffer from wrong hypotheses. It strengthens through them. Planet 9 is not a failure waiting to happen. It is a testable idea rooted in dynamics. Its value lies in the rigor of its examination. Now step even further back. Whether found or not, the search for Planet 9 illustrates something about humanity's relationship with the unknown. We are drawn to edges. The edge of continents, the edge of oceans, the edge of space. And once we believe we have mapped an edge, we feel an urge to confirm it is real. Planet 9 represents the possibility that our solar system's edge is not where we thought. It is farther, wider, less tidy, and that realization aligns with a broader truth. The universe consistently exceeds our first assumptions. We once believed Earth was the center. Then we learned we orbit the Sun. We once believed the Sun was central in the galaxy. Then we learned it is one star among billions. We once believed planets were rare. Now we know they are common. Each step reduces certainty and increases scale. Planet 9 fits that pattern. It asks whether our planetary system is simpler than others or merely incomplete in our observation. And there is something poetic about a hidden planet orbiting silently in darkness, completing its slow arc while civilizations rise and fall, while telescopes sharpen, while theories refine. If it exists, it does not hurry to reveal itself. It has no reason to. Its orbital period dwarfs human history. Its motion is measured in millennia. We measure in decades. In that mismatch of timescales lies humility, and humility is essential in astronomy because the universe does not adjust to our timelines. We adjust to its. Now imagine the coming decades. The Rubin Observatory scans the sky repeatedly. Infrared surveys improve. Data accumulates. Patterns clarify. Perhaps one night, analysts notice a faint object shifting consistently in predicted coordinates. Follow-up observations confirm motion. Orbital modeling matches gravitational predictions. Planet 9 becomes real. Or perhaps years pass and no such object emerges. Clustering weakens. New objects fill in random orientations. The hypothesis recedes. Either way, knowledge advances. That is the quiet triumph of this story. It is not about dramatic discovery. It is about disciplined curiosity. Planet 9 is a reminder that the solar system remains dynamic, not in explosive change, but in interpretive evolution. We refine our map, we adjust boundaries, we test structure, and in doing so, we better understand how planetary systems form, evolve, and stabilize. In the end, the question, is Planet 9 still out there, may remain open for years. But perhaps the deeper question is this: are we willing to look long enough? Because some mysteries do not yield quickly. They require patience, wide field surveys, long exposures, careful statistics. Planet 9, if real, rewards persistence. If not real, it rewards skepticism. Both are virtues in science, so we close this journey not with a definitive answer, but with clarity. The outer solar system contains patterns that challenge simplicity. Those patterns suggest, but do not guarantee, a hidden massive world. Searches continue, models evolve, data grows, and somewhere in the deep black beyond Neptune, either a super-Earth circles quietly, or the empty space itself waits to teach us something subtler about gravity and perception. Until that faint moving dot is confirmed or definitively ruled out, Planet 9 remains what it has always been, a possibility written in orbital motion, a reminder that even in our own cosmic neighborhood, the darkness may still hold structure.